So today the topic is the nuclear magnetic logs for hydrogen serpentinite for hydrogen reservoir characterization in serpentinite rocks. So the subsurface hydrogen gas detection, reservoir characterization, and stratigraphic seal integrity evaluation. Starting for a brief summary of geologists underline that the stratigraphy of the area, measure stratigraphy of the area, formation is surface rock is claystone, thickness around 100 meters, is the ultimate shallow fluid barriers preventing vertical seepage, extracted value from nuclear magnetic logs. We have a clear petrophysical signature. T2 peaks is minus than 3 milliseconds, high clay boundary water CBV. The primary cap rocks of system is represented by limestone with medium thickness of 18 meters, structure trap directly overlying the serpentinite system, very low total porosity, minus than 3%, isolated micropore peaks of 5 microseconds. The target reservoir is built up by serpentinite rocks. The target zone is a hydrated ultramafic system, contains hydrogen in fracture nectars. The bimodal T2 with high diffusion HAC2 gas signature. So hydrogen generation in serpentinite rocks. So the general history, that is the abiotic production. Serpentinization involves oxidation of some minerals like ferrous iron or in olivine, pyroxene ferritics in magnetite, presence of fresh water reducing water to generate free molecular hydrogen in gaseous states. The structure storage. Natural hydrogen is trapped within high fracture serpentinite networks, faulted zone, and active tectonic shear system beneath tight cap rocks. The pore phase states hydrogen gas exists as highly mobile free gas phases within macroscopic fracture dissolved in saline aquifer or pore waters, or weakly absorbed on sheet silicated margin. So this is a general structure of measured trapped hydrogen system. How nuclear magnetic logs works for fluid discrimination. You have a clear the presence also of different phase, gaseous phase as hydrogen that is very small molecular, and waters, and we can have also water with presence in near high temperature. So nuclear magnetic is directly proportional to activity hydrogen proton density. Liquid water as a response clear to 1 points. For compressed hydrogen gas, the HAC is significantly lower and pressure depends typically between 0.1 to 0.3 for reservoir condition. This distinctive porosity deficit is diagnostic for the gas presence. So when you have and after I will show you how to calculate the hydrogen index. When you have this typical value, you are or is called also deficit of porosity, you are diagnostic for the gas presence. But to be useful the natural storage of reservoir, we have also to much more important analyze the diffusion coefficient, the natural diffusion coefficient of the rocks. So this is the inverse of permeability, and you can do this for the transverse relaxation of in rocks combined bulk, surface and diffusion relaxation mechanism. Because molecular of hydrogen has exceptionally high self-diffusion coefficient, diffusion dominates in two low magnetic gradients. So this is why one of the best motivation, because we are applying nuclear magnetic logs, especially in really fracturated reservoir, serpentinite reservoir, because this is highly sensitive to diffusion of hydrogen with this formula that links the two-time relaxation sensitive of molecules of hydrogen to the diffusion coefficient, to the density bulk of rocks, and other parameters. Hydrogen relaxation paradox. Spin rotation and interactive dominance. So what you are really measure is the spin rotation interactive dominance. Unlike standard hydrocarbons or water, bulk hydrogen gas exhibits extremely rapid longitudinal and transverse relaxation due to powerful spin rotation coupling. At a typical reservoir pressure between 5 to 10 megapascal, bulk to time relaxation is very short, between 5 to 10 milliseconds. So we are developing a new class of nuclear magnetic logs for this special application for hydrogen detection. Because these overlap directly with the clay boundary water, standard T2 cutoff sometimes fails, so we need to improve a next class of nuclear magnetic logs instruments. A multi-dimensional nuclear magnetic logs is strictly required to resolve this gas signature. Different way to perform nuclear magnetic logs. We have two standard ways to perform the nuclear magnetic logs: dual echo spacing, the dual TA, exploit the diffusion relaxation contrast. So we are exploit the diffusion relaxation contrast. We are make a comparison of diffusion coefficient in two different times, operating with the different echo spacing. Under a constant tool gradient results in server of T2 attenuation specifically for more highly diffusion hydrogen phases, making it easily distinguishable from stationary fluids. So the second is a spectral mapping of reservoir. This is an advanced method directly resolves the overlaps of different recorded times or relaxation of molecules, especially when you are matching different physical phase or mixing phase, because the interval gradients shift to T2 relaxation time, but do not altering the first time of relaxation. Acquiring dual parameters map resolve the true gas signal. Hydrogen plots in a unique two zone with exceptionally high T1, T2 reaction and high diffusion coefficient. Nuclear logs fluid interpretation matrix. So you have several kind of standard references to value. For hydrogen gas, the hydrogen index must be contained and between 0.1 and 0.3. The typical bulk T1, the typical first time recorded is between in milliseconds is between 100 and 300. The second bulk 2, that is the very turbulent signature for this gas. So we are working for this moment to develop a new class of nuclear magnetic logs that is allowed to record this short signal between 5 to 25 milliseconds. We generally have self-diffusion coefficient diffusion around 150 and 200. Extreme signature for hydrogen gas in serpentinite rocks. different if you are working for hydrocarbonates like methane, mapping the reservoir gas, methane gas. Hydrogen index is between 0.3 and 0.6. Typical bulk T1 is 1. We have a high value, easy value to record it, 1000 to 3000 milliseconds. The typical bulk also is too short, but when you can not ignore, but you have to pass of this value, because when you have a high value, or you are sure you are in presence of mixed phase of gas and methane, you can exclude the presence of hydrogen. The fresh reservoir water have a clear signature because they have a high bulk T1 relaxation time and high T2 relaxation time, so very low self-diffusion. So it's very easy to recognize this from this liquid phase to this gas phase. Clay boundary water, CBV, generally have a very low T1 bulk T1 values. It goes on the first target. So the seal evaluation. Seal evaluation is in this case composed by 80 meters limestone cap rocks. The primary seal over serpentinite targets is tight, a limestone of 18 fix. The nuclear magnetic logs show extremely low total porosity, minus than 3%. The absence of any movable fluid signal indicates it tight necroporous matrix, forming an impermeable barrier to highly buoyant and mobile H2 molecules. 100 claystone overbound. Directly above the 100 claystone exhibit high clay bound water but zero permeability, acting the final security barrier to deep migrating gas plume. So we have a first plotting of nuclear magnetic logs 2 times profile, reservoir versus cap rocks. So you have the cap rocks, the limestone, that have this kind of response, this 2 time transverse relaxation time expressed in milliseconds. You have a green, you have a consonant peak in this part, but the signature of serpentinite rocks is much more different, because you have this point that represented the gas peak diffusion. The claystone surface seal is this, and the signature of clay surface seal is this. Is totally shifted by the peak of limestone cap rocks and the peak and the gas peak diffusion of serpentinite reservoir. Introducing the hydrogen index constant. Hydrogen index constant is an expression of the quality of reservoir. The quality of reservoir, it represented like a percentage of available hydrogen can be extracted after the reservoir characterization. So in this case you have a mixed situation, because you have a poor water, methane at pressure of 20 megapascal, and hydrogen to different level, so one at same pressure of methane, another to the minus pressure. So also studying from engineering point the pressure of reservoir, we can allow to develop and facilitate the development. Matrix interface and mitigation, pragmatic mineral interface. So we have also the signature. We have also sometimes the signature of some minerals that give you the signal that this is the presence, that the rocks can be signature, but the presence of some minerals is linked to the presence of hydrogen. Serpentinite rocks contain a substantial quantity of magnetite, or mineral magnetite, and iron-rich phases. This generating intense localized internal magnetic field gradient that will be recorded easily by nuclear magnetic logs at pore scale when magnetized by nuclear magnetic logs. So we have sometimes this trouble. The presence of magnetite can be altered the real value. There will be a signal, but can be also an alteration. It induced to do shortening, interval gradient drastically accelerated transverse dephasing, artificial shortening the observed to do relaxation time, and shifting fluid peaks to the left. This can easily mask the hydrogen gas signature or results in significant errors. Mitigation via T1, T2, and short TA. Since interval gradient do not affect longitudinal relaxation, ratio remain highly reliable, acquiring data and ultra short icon spacing. So minimize the diffusion dephasing. When you have a value of T2 relaxation minimum this value, you can minimize, you have a trouble for the diffusion of hydrogen, successfully isolating the true fluidic properties. I show you the So the trouble of presence of magnetite and mineralization, the ACA2 generation and NMR response, serpentinization and ACA2 potential, the chemical mechanism and geological volumetric. Serpentinization engine. Serpentinization is a series of hydrothermal oxidation. Prima magnesium iron silicate is built up by forestesite and phalaite olivine, that are olivines groups. Breakdown chemical to yield serpentinite, sheet minerals, magnetite, and free hydrogen gas. So the typical reaction that is a reoxidation reaction of ferrum iron is this. The reduction of water molecules is given by the ferrum silicate by 7 molecules of water that generated this new hydrating ferrosilicate, but hematite and free hydrogen. So this is the basic way, natural way that was generated hydrogen. The simplified phalaite reaction maps the stoichiometric links. To every mole of magnetite formed, 1 mole of gaseous molecular hydrogen is generated. Hydrogen generation capacity. How many hydrogen we can generate? So this is another important question. If you have a block of 1 meters cube of phalaite rocks is this. So the phalaite rocks, we can generate it for 1 metric cube, you can generate 1.5 kilos of hydrogen. So reservoir chemical limits. The total volume of hydrogen gas that can be generated is chemical capped by the initial volume of the reactive phalaite. So you need to consider effectively for the economy of the reservoir that you don't lose the mineral information and the petrographical information, because petrographical information in this case is essential to a prevision of how long will be the life of hydrogen production with this geological context. If you have a total volume of an estimation of total volume of 1,000 mils of phalaite, you can have an high annual production of hydrogen. The reaction is high temperature dependent, optimizing in a thermodynamic window and this reaction is also governed by the thermodynamic window between 200 Celsius degree between 300 Celsius degree. At this condition, reaction kinetics rate minimized generated abundant hydrogen plumes that migrated upward into shallow structural trough, so in the seal of trough. Serpentinite water bindings. We have also much more other important minerals that you can analyze through petrographical sampling: lazardite and antiquarite sheets. These serpentinite minerals contain high structural hydroxyl water fraction, about that is generally between the 30% of total weight. Nuclear magnetic logs cannot resolve only cannot respond direct to this. We can have only an indication, but you need to improve with sampling petrographical analysis. Nuclear magnetic logs cannot resolve this hydrogen direct because it's chemically boundary driven reaction with crystalline latex. Moreover, the sheet-like microporous geometry of lazarite and antiquarite clays retains significant volume of clay boundary water. With relaxes extremity time, so you the other trouble is to developing a new class of nuclear magnetic logs that is able to record to a second to relaxation time minus than 1 milliseconds. Fibrous crillosite matrix. The crillosite exhibit a distinct rolled tabular nanostructure. Capillary force allows mineral tubes tightly restricted pore waters. The nuclear magnetic measure this capillary bounds phase as a broad BAVI signature. Identify this mineral structure is critical as capillary force impede the relative permeability of both water and migration hydrogen gas. So it is an image from laboratory petrographic mineral mapping. The thin section of crystalline networks. The microscopic view reveals complex lazardite mesh structure intertwined with dark, opaque magnetite, veins running along relictive fracture, impact on pore geometrics. The serpentinization causes a massive solid volume expansion. So the process, you need to study the process, underline the process of serpentinization, because we have generally created a mass expansion. This expansion induces microstructure fracturing of the matrix that can be a wave of diffusion of hydrogen. This newly formed microfracture provides both storage space and high permeability pathway for mobile gas hydrogen, as we just said. Go to the magnetite trouble. So, serpentinite rocks are still rich in magnetite. Magnetite is really sensitive to excited to the NMRL tools. Magnetite is highly magnetic. It generates itself and intense localized magnetic fields when exposed to downhole NMRL magnetic tools. How recognize the real values? How differentiate the real values of natural signal magnetite to the other mineral or to the presence of hydrogen gas? So this is a really important question, and this is why we are trying still to develop a new class of nuclear magnetic logs. So the physical sociability construct between mineral magnetite and agent pore fluid dominated by the transverse relaxation. We have several transverse phasing. The total observed transverse relaxation rate is accelerated by internal gradient term. So the advance to the logs must isolate this mineral interface. So you need to isolate the signal of magnetite, because magnetite totally distorts this, the real value. Which are the critical mineral that we are generally present in serpentinite rocks, and that we can produce the dominant value that distorts the real targeting. So phyalite, as we just say in the previous part, is the basic mineral that produced the major quantity of hydrogen. So recognize the phyalite, that will be a primary exploration signal that we are a potential reservoir of hydrogen. Olivine phyalite, with this formula, primary reactive provides Fe2 source for reduction, which is the dominant nuclear magnetic log 2-time response signature, minimal matrix defacing, and standard T2. Lizardite serpentinite, we have a reaction production makers of hydrogen progress, ultra fast structural CBV dominance, the magnetite and FL co-production with IK2 and direct indicator of change, accelerated to the phasing with the IG G int. We have also the trouble of brucite, because also the lizardite and the brucite can, when are hit, when are cut, the linking between atoms of magnesium and oxidryle, you have a free possibility to have a free hydrogen. So the second product, generally we have brucite in the trap. So brucite generally was linked to the trap. So secondary product traps structural magnesium, static, no direct signal. So we have no direct signal. So the really trouble is this. So it's clear that isolating hydrogen in serpentinite reservoir and processing in correct way logging to have a clear difference of signature between magnetite, phyalite is an advance in processing protocols to recognize purge, filter magnetite and phyalite signature and brucite matrix signature in NMRLogs and NMRLogs data reservoir. So the paramagnetic reservoir controls, deconvolution strategies for magnetic, because natural magnetite induce magnetic field depending on the phasing. So the magnetite is highly magnetic mineral byproduct for serpentinization when exposed to downhole magnetic, and exact is a localized magnetic pole. This generates serve localized internal magnetic field gradients in addition to pore spacing, dramatically exceeding the tool's external background gradient. The transverse phasing, because the diffusion relaxation term is proportional to the square of the presence of magnetite, it accelerated the two-time relaxation. So, analyzed the difference between two instants, you can square and the line which is the present and the quantity of magnetite in your reservoir. This dephasing shift fluid signal to left, causing mobile hydrogen gas and water to mimic tight bound, fasting relaxed clay bound water phase. So you need to go to produce the dephasing filtration protocols, an equal spacing for pulsing of 0 to milliseconds. So new the new necessity of developing a new class of nuclear magnetic logs for this purpose. Now filling internal gradients. The primary method to purge magnetite interface is minimizing the echo spacing during well logging acquisition. By forcing TA to extremely short direction, the diffusion dephasing term is mathematically minimized. This restores the actual relaxation distribution, separating the true hydrogen gas phase from artificial bound water signature. So you can have an artificial signature in nuclear magnetic logs given by the presence of magnetite and boundary waters. Phi Elite, so the baseline matrix, Phi Elite is the baseline matrix generally in hydrogen production and reservoir hydrogen. This Phi Elite is not iron-rich aluminum reacted that driven the abiotic syntax of hydrogen during serpentinization, and there were also an image of Germany Phi Elite. It forms that non-hydrated rocks frameworks. Unlike magnetite, Phi Elite is still a weak paramagnetic rocks and does not generate self-locate field gradients. So if you have a sampling of your reservoir with and easily petrophysical analysis mapped the presence of Phi Elite, you can ensure that Phi Elite will be the source rock, one of the best of Phi Elite will be one of the best source rock. So the mineral Phi Elite will be one of the best source rock, especially if you have just this reaction. So the Phi Elite is this. If you have the presence of water, enhances this reaction, this oxide reaction, and you have a natural production of hydrogen. So Phi Elite will be the source rock of hydrogen or natural hydrogen. Using nuclear magnetic logs to identify this tight, non-responsive framework allows loggers to calculate the true active fluids volume while pursuing solid skeleton density cross-plot anomalies. So the real trouble is the dephasing of magnetite. The presence of magnetite is still sometimes given a troubleshoot value to nuclear magnetic logs because it introduced magnetic fields. Bruchite and trap signals. You have also to analyze the characteristics of traps, identify lattice structure traps and isolating fluid signature. Bruchite, this is structure trap, lattice bound protons. Bruchite also contains a second part of type subhydrogen groups located within its crystalline lattice framework. This is a no reservoir traps. So that means this hydrogen is free to evolve without the traps, to dissolve naturally and with natural porosity in the upper terrain. Ultra fast decay times. So because the hydroxyl proton are physically bound with a solid, they dipole interaction are extremely strong, causing decay time to under 10 microseconds. 10 microseconds. We are working under 10 microseconds. So you are working in a very, very short time, 10 microseconds. 10 microseconds also need new class of nuclear magnetic logs. Standard filtering windows. So the standard logging tools have a minimum echo spacing between 0 to 1 milliseconds, make Bruchite lattice signal completely invisible. So today with actual technology we are not able to recognize the Bruchite signals, and we are not able to study the decay and evolution of Bruchite. This serves an automatic physical filter. So this is an advanced point of applied research. Mineral resonance diagnostic table. go to this summary table, the subsurface component, the magnetite matrix, hydrogen state. We have a dry skeleton, typical NMR2 range, accelerated dephasing, G server, acquire the pulsing and the isolated protocol. In this case, you need to echo spacing minus than 0.2 milliseconds. The Fayolite matrix. So Fayolite matrix, you have non-dry reactive based. So we have a baseline. The typical NMR2 is baseline skeleton. Establish cross-plot zero porosity mineral density limit. Filtered automatic by tools did time lines. Hydrogen gas, the fluid molecular gas, have generate this kind of signal between 500 to 450 milliseconds, but which is the trouble, the vulnerable to dephasing. So you need to apply the dephasing processing to separate the signal of magnetite and also the signal of magnetite and also to brucite to recognize the effective volume, effective free volume of hydrogen gas. Apply to the diffusion weighted deconvolution to isolated peak. Nuclear magnetic spectrum low. The nuclear magnetic spectrum raw versus filtered Akadu. The transverse relaxation time. So you are record the transverse relaxation time in your nuclear magnetic logs. The raw spectrum is evenly shifted to the left orange due to the effect of magnetite presence. Applying to short echo sequence and diffusion deconvolution, you can purge these effects, isolating the true hydrogen gas peaks. The true hydrogen gas peaks is generally near to 25 milliseconds. When you have a peak around 25 milliseconds and you are dephasing all the signals, you are sure that you are isolated the peak and the presence of hydrogen. So we have a raw deconvolution flow, echo selection, run CPM log at multiple echo spacing times. You can run the spacing log with different echo spacing time between 0.1 to 1.5 milliseconds. So you need to be able to recognize the very short interval, a very small interval, to establish gradient sensitivity. So you need to also to provide a gradient mapping, the structural mapping of magnetite volume to solve the localized internal gradient field. So if you are able to isolate the volume of magnetite and to isolate the volume of fayolite, you are sure that in internal serpentinite rocks, you are sure which will be the production rocks of hydrogen. And so you make a prevision of life of reservoir, a prevision of life of production of hydrogen. Deconvolution filter, apply diffusion weighted inversion to filter out accelerated the phase fluid elements from solid brucite bounds. Isolating H2 signal, reconstruction the correct 2 signal spectrum to yield to the true free hydroxyl index and reservoir porosity. So you need to isolating the signal of this. To do this, you need a mathematical formulation at the applied deconvolution, the total transverse relaxation, the T2, to isolate the mobile hydrogen, we must solve the free constituent complex of relaxation rate with this formula. We have a skeletal gradient separation. So we decouple the total gradient term into external tools and localize the internal mineral component. G total by GTX plus C for delta X for the magnetic gradient. Identify the high diffusion phase by evaluating the system response over varying echo spacing. This slope, because it represented a equation of Retta. This is an equation of Retta. This slope, the 1, 2, that is essentially the slope of the T2 isolated diffusion coefficient identify high diffusion phase. We can go through an example of how isolating this. So in this second part we are showing effectively how working to isolating hydrogen signal in NMRL well logging. Practical protocols, processing workflow in case starting in serpentinite reservoir. So this is an advanced subsurface physical and hydrogen consortium. The target is ferritic serpentinite and deep crystalline hydrocarbon basin. Multi-fluid, so we have generated the multi-fluid overlap paradox. In a typical sedimentary or crystalline play, the nuclear magnetic log relaxation response transverse relaxation time T2 measure at the rates at which hydrogen protons transfer energy back to their environment, bulk, the surface relaxation, and the phase due to magnetic diffusion. Free molecular hydrogen possess a very fast bulk relaxation rate, as we just said in the previous part. Displaced its natural T2 relaxation signature directed to 10 to 100 milliseconds window in the identical space occupied by capillary boundary water and lighted hydrocarbons. So the typical range is very short. You have a climbing bounce between 0.5 and 0 and 3 for milliseconds. Diffusion coefficient is 10 elevate minus 6. So the ratio, the rapport between T1 and T2 is between 1 and 1.5. Principles, so extremely rapid decay, minimize micropore bound gas. For compressed hydrogen gas, you have a typical range between this value. The diffusion coefficient is much more different between other coefficients. The ratio between T1 and T2 is between 4 and 10, high diffusion and ratio moderate. For heavy oil organic, you have a really high coefficient diffusion, and typical T2 relaxation is more between 1 to 10. So rapid relaxation overlapping with clay boundary fluids. K petrophysical concept. Diffusion while 1D transverse relaxation spectrum of compressed hydrogen gas directly overlaps with boundary water is it itself coefficient is nearly an order or magnitude between these values. The impact of internal field gradient. Serpentine rocks have a natural contains of quantity of magnetite. Because magnetite is highly ferromagnetic placing it with static polarizing magnetic field, and NMRLogs tools induce massive localized internal magnetic gradients. The protons diffusing past the microscopic gradients dephase instantly, artificial shortening the apparent T2. The dephasing smudge that hides the fluid signature. Processing protocol and multi-dimensional mapping. To cleanly separate the signal of interest from noise and overlapping fluid, petrophysicists utilized advanced frameworks and multiple dimension inversion mathematical solver. The dual parameter acquisition. You need to consider the dual TA and dual TV. Standard logging sweep with the sweep are fixed to echo spacing TA and weighted TU. To isolate hydrogen, we must alter these parameters during logging. Dual TA protocol by acquiring one run with an ultra echo spacing. You need to be under 0.25 milliseconds and another with a longer spacing time. With this, we maximize the diffusion induced decay. Because hydrogen gas high diffusion, it is a signal will experience server amplitude loss in T2 sweep compared to water phases igniting in presence. Dual protocol polarization. We need to create a dual protocol polarization. Hydrogen gas relaxes low in the longitudinal direction, so in T1 long, often with times of 1 seconds at reservoir condition, compared to clay water. Utilizing a short wait time near to 300 milliseconds, you completely polarize the water, but fails to polarize the gas. So if you polarize the water, you are not polarize the gas, and you are not able to recognize the gas. So this is why you need a new polarization system for NMRLogs, subtracting the short TV spectrum for a normally full polarized long TV spectrum yields a differential spectrum contains only the gas signal. In this way is the only way to isolate it and to have a clear recognize of gas signal. 2D time spectral mapping. The ultimate isolation methodology relies on 2D D2 time and T1 ratio spectral deconvolution. The process map amplitude simultaneously against relaxation time and diffusion coefficient. So in this plot you have a T2 times expressed in milliseconds. You have diffusion. You make a rapport, a link comparison between 2 time and diffusion coefficient. So it's actually you are not really able with these technologies to isolate the signature of hydrogen gas, because hydrogen gas have a high diffusivity, especially when you have a fractured reservoir. Have a high diffusivity because molecular is too small, so is out of this line. This line represented the slope, the medium slope average of 2 time relaxation. Along this line you have CBV, BV water, free water, but isolated gas is out of this, so you need to effectively have the possibility to remake, to use this diffusion and line a microseconds to isolate this. So to isolate this you need a protocol, a different protocol. Mathematical isolation. You can clearly use mathematical tools. The total observed transversal relaxation time is the sum of bulk, surface and diffusion induced relaxation time for hydrogen in a field gradient. The equation resolves this. Y is this gyromagnetic ratio, the proton, Ta is the echo spacing, G is the magnetic field gradient. So magnetic field gradient is much more important because if you have the presence of magnetite, you are able to isolate these parameters and estimated the contribute of magnetite to this. So it's one of much more important that you need to develop a new class of nuclear magnetic logs. And D is the diffusion coefficient. D and second is extremely large, running dynamic logs inversion, isolating the third term diffusion, and mathematical peels away from overlapping water signature. How we can do this from raw to filter data? You have an uncorrected log. So below the showcase a quantitative example of raw uncorrected serpentinite reservoir logs result compared to post-purge filter calculation. Uncorrected log, the presence of 8% of microscopic magnetite with serpentinite create a strong internal magnetic gradient field. Creating a strong magnetic internal field, you have an alteration of total value of T value relaxation. At standard echo spacing of 1.2 milliseconds, the diffusion term dominates the decade. So results, T2 curves shift leftwards, dropping below 3 milliseconds. So the results of presence of magnetite and not correct interpretation is the shift of curve. So this is the raw phased signal. The reservoir appears dry tight. In this case, it seems no possibility. Reservoir appears dry and tight, and the clay saturated. Interpreted is no zero free gas. So finally, if you are using this approach, apparently there is no gas. 100% of clay boundary water. But applying new class of tools, utilizing a ultra short echo spacing, you need to utilizing a ultra short echo spacing 0.25 milliseconds, minimize the gradient, the phasing time, and transferring focus back to the fluid properties, you have a multi-wave polarization. Then separate the gas components. Results, we have a correct spectral inversion and plotting, and high distinctive peaks at 14 milliseconds with elevated diffusion. So in this way, it seems to be this situation, but the real situation is that isolated gas peak. This corresponds to a 40% free gas hydrogen. It's incredible. You have not a free gas, but you have 14% of gas hydrogen in the reservoir, and you are not considered the possibility of Fayalite contribution. So hidden with the raw noise. Dynamic porosity reconstruction. With the hydrogen peaks correlated map and isolated the TT1 filter, the total free hydrogen porosity can be extracted. Standard petrophysical density porosity is highly inaccurate in serpentinite due to the fluid's density and iron mineral weights variation. So the NMRLogs isolated volume provides the only reliable baseline, and the formula is that to calculate the effective percentage and volume of hydrogen. Where is the hydrogen index correction factor high dynamic for gas under high gas pressure? These steps ensure the X value of a commercial gas estimating, omitting boundary hydroxyl molecules in the background clay and Buchite matrix. So, if you are conducted the standard logs with the standard techniques, it seems not to be the possibility to extract hydrogen, but you lost much more information about the presence of Fayalite, the presence of Buchite, and the possibility of evolution of this trapped system. So it's clear a panoramic overview of how isolated the practical isolation workflow and filtered and have a corrected data, a corrected spectral inversion that relieve a distinct peak of 14 milliseconds with elevated diffusion. Okay, we just do this. Nuclear magnetic. Okay, we say this. How we can calibrate logs is essential. Have a XRD core scan. XRD core scan and SCAL petrophysical analysis perform 2D SCAL petrophysical analysis test on saturated cores to establish shift fluid cutoff. quantify weighted fraction for XR scan is placed to quantify the weighted fraction of olivine, serpentinite minerals and crystalline magnetite. The susceptibility mapping measures the volumetric magnetic susceptibility of core plugs to define the G bounds. The skull analysis is structured for on a saturated core to establish shift fluid cutoff. If you have a saturated core, you can have also the shift cutoff, and we analyze in the next step. Aids to charge inversion, map dynamic FFA volume to localize fracture zone, tracking mitigated H2 plumps. So the ACT2 charge inversion map dynamic FA volume is the plus. You need to mapping the all of fracture, the tracking the source rock, this is generally the rock that contains fryolite in this case, and also tracking the probable plumes of migration of hydrogen, which will be the system for subsurface migration and diffusion. Buoyancy-driven natural ascending generate an immense upward buoyancy force within water-saturated matrix. Capillary force balance in infrastructure matrix blocks. Migration is governed by the balance between buoyancy and capillary entry pressure. Diffusion loss and Fick's law. So we have some specific characteristic of hydrogen that is a high diffusion as small molecules within extremely small kinetic diameters. Hydrogen diffuses through crystalline cap rocks from 2 to 10 times faster than methane. So these molecules have a really fast diffusion. So it's easy to migrate. You need also to consider this aspect. Is easy to migrate from source rocks to cap rocks and others. The rapid loss mechanism makes geological contains challenging. Diffusion occurs directly through structured crystalline latex and water-saturated microporous channel. Effective diffusion. Fick's first law describes the steady flow transportation. In porous, the effective diffusion is related to by the porosity and tortuosity of rocks. It's clear that. Which characteristic have also hydrogen molecules? Have a low viscosity, have a behavior like a low viscosity fluid. So it's not a standard gas. It's not a standard gas because its physical behavior is similar to low viscosity fluid in this system. You have viscosity at 10 megapascal pressure is around 10 megapascal is around the pressure that you are able to record it to 1 kilometers. At reservoir condition, gaseous hydrogen has a viscosity of less than half that methane, and almost it's clear that a viscosity less than methane and almost 2 orders of magnitude lower than water. So there's extremely low viscosity increase fast the mobility ratio within the reservoir rocks. Consequently, hydrogen flow with minimal shear resistance, leading to potential turbulence even with tight geological fracture and micropores. In this situation, the cap rock seal retention limits, which is the limits. The limits is set by lithostatic pressure and also compressional pressure if you have, for example, an anticlinal system. So the cap rocks, if you have, for example, cap rocks made build up but hyalite or soft rocks, generally capillary pressure is measured than 18 megapascal. The effective permeability drastically decrease to 10 elevate minus 21. And it represented a perfect seal because you have a zero capillarity and absolute barrier. With anhydrite shales, you have a capillary pressure driven in this case by the depth of cap rocks and the density of rocks and effective lithostatic pressure between 5 to 12 megapascal. The effective permeability is this: high effective low diffusion risk, minor microscopic boundary loss. The crystalline limestone, you have 1 to 30 megapascal. Semi-permeable, high risk of cap displacements over geological time. Compacted silestone. For a compacted silestone, you have 0 to 1.8 megapascal. Inadequate, continuous rapid capillary leakage action as migrate pathway. So when you have a limestone, both crystal and compacted, you have a possibility to displacement over geological time or migration. It's clear that when the capillary pressure goes down 5 megapascal, when capillary pressure goes down under 5 megapascal in cap rocks, you can have the migration. Overpressure and containment. The fluid density control, hydrostatic and lithostatic pressure regime governs gaseous density and reservoir capacity. Under high pressure, hydrogen compress was be compressed and maximize storage density. So you have some leakage in which will be storage. The tectonical induced overpressure can exceed the cap rock's minimum mechanical principal stress. We are triggering as microfracture, and the microfracture can be driven in the diffusion of hydrogen. Because of hydrogen is low viscosity, this leads to rapid escape through self-propagating through the fracture. Which is the reservoir trapping mechanism? In general, we can have structure trapping, capillary trapping, and minimal absorption. Structure trapping for hydrogen buoyant is gas accumulated in anticlinal domes, fault blocks, and stratigraphical pinch-out. This is the principal structural trapping: anticlinal domes, fault blocks, and structural pinch-out, directed enough to the tight regional seals. Capillary trapping. During water inhibition, capillary pressure snaps of hydrogen bubbles within narrow porous necks, what retains the hydrogen as immobilized residual gas. Mineral absorption. The clay sheet structure and organic matrix provide weak physical absorption, slowing macroscopic migration rates through molecular drugs. So this is a totally different pressure, a different process. As we just say, with capillary trapping is governing by the density of rock, the depth of seal trapped, and hydrostatic pressure. When this capillary pressure goes down 5 megapascal, you have possibility to diffusion over geological time of capillary leakage and acts as migration pathway. Mineral absorption, you have a clay sheet structure, organic matrix that provide weakly absorption, slow macroscopic migration rates from molecular drugs. We are plotting the gas dense versus pressure trends. The reservoir pore pressure so is less, much more less than methane reservoir. So if you are make a factor, if you make a comparison between two gas systems, one is driven by methane, another is given by hydrogen. Probably from a security factor, hydrogen reservoir works at low half pressure of methane reservoir. So it means that a different approach, because as you just say, we have a very high velocity of diffusion. It is not low viscosity moleculars, so but is much more secretive. Migration system assessment. So you need charging tracing, map deeping abiotic generation sites or mantle degassing pathway to trace initial charging lines. Sometimes you have the periodotite, that is a very deepest rock around 30 kilometers. So the migration initial from a deepest pathway. The buoyancy modeling simulated upward migration vector based on fracture connectivity and local pore water. Cap rock stress scan, measure capillary entry pressure and minimal principal horizontal stress of target sea rocks. The pressure profiling. Establish hydrostatic limits to prevent the overpressure situation or damage the reservoir or microfracturing. So in this case, for creating, for example, for enhanced production microfracture, we really recommend the Schlumberger system, that is the electrofracturing. Two spectral mapping in subsurface hydrogen reservoir. Go to the geophysical approach to the spectral mapping of reservoir. So in the first phase, we analyze the pathway of migration. We see through nuclear magnetic logs and necessity a new type of magnetic logs, the mapping of source mineral like fayalite and the interference of magnetite. Through geophysical other logs, we are going to do 2D spectral mapping in subsurface hydrogen reservoir. Which is the Lamor frequency. Lamor frequencies is the precise frequencies at which nuclear magnetic moments spin of hydrogen will be in resonance to the instruments. In subsurface nuclear magnetic logs, these frequencies act the resonant gateway for energy transfer. Mathematical value. The frequency is directly proportional for the magnetic field strength governed by the Lamor equation. So the Lamor equation describes this frequency. For hydrogen, and so this is the explication of how we can detect hydrogen by nuclear magnetic logs with this approach to this spectral mapping. For hydrogen have this constant ratio is equal to 14.62 megahertz Tesla. So this unit represents frequencies by intensity fields. It is a particular physical units because this is a ratio between frequencies by intense field. Downhole tools operates at low fields, 0.5 Tesla, yielding a typical resonant frequencies of 2 megapascal. It's clear that there is another trouble. In reality, the reservoir is not continuous in x, y, z. You have some anisotropics. You have, for example, the longitudinal polarization. The minimum required weight is this. Multiply 3 for first times of relaxation. Polarization describes the build-up of the microscopic magnetization along the longitudinal axis when exposed to the tool's permanent magnetic field. This is an exceptional thermodynamic alignment process characterized by the constant T1. If the logging tools pass too quickly without allowing sufficient polarization time, the hydrogen nuclei will not fully polarize. So if you have not the time to polarize the hydrogen, you are not able to recognize the presence of hydrogen, leading to severe underestimation of the subsurface fluid volumes. Radio frequencies, pulse physics. An RFR pulse is an oscillating electromagnetic field applied by perpendicular to B01 at the exact Lamour frequencies. A highly calibrated 90 angles degree pulse tips the longitudinal magnetization entirely into the transverse plane. Because magnetic field we are also refocusing the pulse at different angles. At 118 pulse is subsequently applied to invert the phase's spin. This inversion causes the spin to recover converge, generating a coherent miscible signal peak called a spin echo scene. Typical pulse duration range between 10 to 30 microseconds. 10 to 30 microseconds require high electrical power. So you need really two new class on nuclear magnetic logs to conduct this analysis. The spin echo cycle, the CPM sequences. Generally we operate in this way. 90 angles degree RF pulse, magnetization is tipped for 30 seconds, install maximum correx. After you have a relaxation time, you measuring time in homogeneous local fields causing the spin to permit to the atoms to have a realign the spin, pass it to another phase. 118 RF pulse applied all time flips the spin across the transfer axis to reverse the phasing. So this part is essential to purge magnetite fields. Because why? Because magnetite have different times first to time of relaxation. It means it remains on magnetic field. It still continues emitting magnetic fields, has itself magnetic fields. We are reshaping T, spin full coverage at T2 and generating a district miscible spin. So the echo spacing it defines itself the time between adjacent spin echoes. So you have a spin echoes for the excitation of magnetite, a spin echoes for excitation of hydrogen. Hydrogen reservoir is typical T value. I'll keep it extremely short, 0.1 millisecond to 0.5 millisecond to capture faster decay signal. So you need to have a very highly sensitivity to capture this fermitor signal. Quantify free hydrogen volumes. So finally, all of companies want this data. How was the volume of free hydrogen can be extracted? This is the final question that you need to answer. The total initial amplitude of NMR transverse decay curve is directly proportional to the total density of active hydrogen protons in the sensitive volume of rocks. These relationships allow geophysicists to calculate lithology independent total porosity. Moreover, when free gas is present, the low density at gas phase results in a severe underestimation of physical pore space. So, what kind of information given hydrogen index? Hydrogen index is the accurate calculate of the actual free gas hydrogen presence. But it not means that you can extract all of free gas. It's clear that you need also to consider the reservoir engineering sustainability. The nuclear magnetic logs amplitude porosity must be corrected with the hydrogen index. Because gaseous molecular hydrogen has a low proton density compared to liquid water. So as we just say, if you have an Fayalita rocks, that is the generated rocks, and we have a high quantity of water, so you need to correct this because you need an estimation in time of the production of hydrogen. The typical reservoir can range between 0.5 to 35 depending on the pressure. Relaxation time scales. Okay, analyze the relaxation time scales. As we just said, typical for free hydrogen gas, T1 is 100 to 300 and 5 for 15 meters. Highly accelerated spin rotation and gas diffusion. The second, spectral mapping concept. How we can build spectral mapping concept? To build a 2D spectral mapping concept, you need to mapping in all of the direction the T1 and T2 relaxation time by clear. When you are producing mapping, you have just to pre-processing of logs, isolating all of value from magnetite and like this, and finally you can produce the T1, T2 map. By systematically variation of the polarization recovery, we resolve independent two spectra. Since internal rock gradient do not affect to the effect of magnetite or the water influence or like this. D2 mapping correlates the diffusion times. So this mapping, a second mapping is diffusion to time mapping. What that means? It means that in this map you are showing a static, you are showing a photography or animation or how will be the reservoir evolution, which will be the measured path wave, measured drainage path wave of hydrogen, utilizing the tools built in static magnetic gradient separating the fast diffusion hydrogen gas from heavy hydrocarbons or restricted core. Finally, you have a resolution standard 1-2D distribution completed. You have 2D spectral mapping isolated this phase into district zone, for example, source zone, migration zone, eliminating interpretation ambiguity. How estimating the coefficient of diffusion? Transverse relaxation is sum of bulk, surface and diffusion induced relaxation, isolating the parameters. Two established geophysicists acquired several eco-trains. The eco-spacing. Eco-spacing is a pure data. Eco-spacing is the real data, because eco-spacing given it itself the signal of hydrogen and rocks. By plotting the observed relaxation, the slope of the resulting linear trends directly yields molecular diffusion. So this function is linked to relaxation time, is similar to linear equation. So for hydrogen, the D is extremely elevated between these values. So hydrogen diffusion, as we just say, is a very fast moleculars. So you have a diffusion between these values. To the NMRL petrophysical matrix, which parameters underline, as we just say, the first parameters is the resonance frequencies of hydrogen. So is the Lamor frequencies, proton precession rate in external magnetic fields. The typical range is the 2 MHz, but the frequencies of resonance of molecular is calculated with this 42.58 MHz Tesla. Polarization time, waiting time allocated for signal spin alignment, ensure accurately quantified total porosity. The echo spacing, which is the physical meaning of echo spacing, is the time gap between two successive 118 angles acquisition or RF pulse. When you are in field, what we are doing? Insert instruments, go to nuclear magnetic logs, go to downholes, make maneuver, and you set first pulse to 90 degrees. We are tended 10 between 10 minutes to 50 minutes, start to gap the pulse to 18 to this value, and you need you replied this first at 2 times 19 degrees. You replied after 30 seconds, because after 30 seconds you can set the difference by the magnetite normal and the effect of normal magnetite and the magnetization of magnetite and the value of hydrogen. After, the echo spacing is given by the time to gap this and the typical range for hydrogen. If you have hydrogen, you have a typical range of this. Minimize diffusion loss of ultra-fast defacing. Diffusion coefficient rate of random translation is test. Field operation and tools. This is a typical field operation: transmitter, receiver, gamma ray, vibration sensor, and wear bands. Downhole magnetic resonance tools utilize generally a strength permanent magnetic to project a static field B direct into the rock formation, pass to the mud cake barrier. So the instrument is built up with the coaxial antenna array, transmitted the pulse and referral power, and extract Lamor frequency. Because the field is gradient shaped, tying to the frequency allow measurement of the strict radial shallows and avoiding wellbore fluid contamination. Go to the real case, 3D subsurface spatial modeling and hydrogen reservoir. We have a 25 square kilometers exploration block, so the total area is 25 square kilometers exploration block. An extensive geophysical survey across high fracture ultramafic serpentinite play the delineation major structure fault boundaries in native hydrogen. Integrated the 2D multi-dimensional NMRLog across diagnostic wells has enabled the spatial mapping of reservoir fluid. The structure plate boundaries are capped by regional tide limestone layers and provide the critical sealing mechanism required to retain highly buoyant hydrogen gas. So we have trapped with 2 faults, the cross-section kriging disperse, spectral parameters, the resulting 2D spatial and dispersion maps isolated this daily diffusive gaseous hydrogen signature from bound to power, and you have this limestone 80 meters, serpentinite matrix 80 meters, and estimated point of diffusion or zone of diffusion of hydrogen. This is the 3D permeability slicing model with geological fence diagram from boreal data. The 3D slicing applying high permeability conduit pathway ranging from 30 to 35 milldarcy aligned along tectonic fracture axis, while tight matrix remain under 1D. 3D diffusion field mapping. You have also to build the 3D diffusive field mapping. This is like horizontal and vertical to monitor the structure boundaries of the gas couple. In this spatial relation is highly elevated, free hydrogen gas saturation reach its maximum concentration because the self-diffusion coefficient. Gas is more than another magnitude higher than methane and porous waters. It's clear, as we just underlined, one of the characteristics of the hydrogen is the high diffusivity. This slice diffusivity volume maps that show the structure extent and the gas flows. Free hydrogen volumetrics, the total volume of free hydrogen, which will be the total hydrogen available in this exploration block. The total volume of free hydrogen gas at standard condition over 20 km exploration is calculated using this physical properties matrix. The reservoir expansion factor, so we have also the trouble that you go deep, you have also the easy expansion easy expansion driven by the temperature. Expansion factor is governed by the temperature of 50 Celsius degree and 55 Celsius degree and 15 megapascal over pressure, yielding 1 billion standard cubic meters. So the total estimated available in actual condition is 1.5 million cubic meters of hydrogen. This is a table of parameters: effective porosity structure 8.5%, free gas saturation. We have instead the total volume, the 65% was saturated by hydrogen. So the hydrogen index correction is 0.22, so it's good index, and also the percentage. Average net pay thickness, so which will affect the layer, the thickness of productive layer is around 45 meters. You calculated the native volume. So this is so the actual volume. We not make provision to the long-term production by the presence of phyalite. If you are working in a long time, suppose that the plant, the effective plant will have also reinjection of water and stimulation of the phyalite, you can change this volume. Quantity modeling workflow, iGrass NMRLog. So spatial clicking to correlate two cross-sectional interpolation expected dispersed value between fracture wellbore, 3D slicing modeling, reconstruction, the 3D volumetric field mapping, and diffusive volumetric integration, high corrective reservoir calculation across 20 kilometers and exploration boundary. Fault have their influence. If you are logging and you are cut the fault, there is some influence on NMRLog. Tectonic fault generated localizing fracture damage zone. NMRLogs detect these open conduits through a highly pronounced bimodal signature. That is, when you have a fracture, generally you have a T2 relaxation time measured than 500 milliseconds. So this is a clear signature that in vertical you are tracing a fault. Sealing, gouge and clay smears. In construct, sealing faults segments or gouge zone exhibit several mechanism grain. Animal registers this extreme of 3 milliseconds. Which will be the petrophysical fault log signature. You have a single rapid peaks, bimodal for inner domain, outer zone free fault domain will be this, and the diffusivity and permeability are this zero gas movement. Impermeable seal, permeability, rapid gas conduits. Permeability, native rocks baseline have a permeability of 0.9 milliliter. Instead of this, we have rapid conduits at 250 milliliter for inner damage zone. And for fourth core zone, you have a very low permeability of 0.01 milliliter with zero gas movement. So the rapid gas transition is made in inner damage zone by the so this is the conduct pathway driven by the faulted system. Semiconductivity is in the outer zone. Thanks to the SLB. Go through acquired data. Okay, we are going through the acquired data. In this case, we have the NMRL tools Depth of investigation is this interval investigation. We have a vertical resolution, magnetic field apply, 1 point Tesla. You have a synthetic geological system. You have the NMRLog index plotting by the top reservoir. You have a T1 and T2 this, and also the T2 cutoff, that is much more important. As we just say, T2 cutoff is essential. T2 cutoff is essential for using a fixed transfer cutoff of 33 milliseconds in tight carbonates. In serpentinite, I have a typical cutoff of 6 to 10 milliseconds, and it underlines the time that in which rocks have no magnetization after the induction. You have the NMR diffusion logs with the estimation of diffusion coefficient in plotting in depth. So it's clear that the measured diffusion is around this value. Free hydrogen fluid index, which is the free part, is the reservoir that is under 118 meters. And you have the NMR2 inversion spectrum for hydrogen reservoir signature. You have the amplitude versus the 2-time relaxation in milliseconds. So you are plotting in this graph the relaxation time for surface rock, the claystone, the limestone seal, the serpentinite reservoir, and the free fluids. We have also analyzed the Lamor frequencies. Lamor frequencies for this, the hydrogen reservoir interpretation, claystone a very low index, boundary water dominated. The limestone is intermediate because itself with the presence of brucite produced intermediate hydrogen, T2 below free fluid cutoff, low mobile hydrogen, and serpentinite is a high hydrogen index. We have an intermediate hydrogen index because there is the presence of brucite. Low 2 is an high free fluid index, molecular signature. Go to next is the CPM, serpentinite hydrogen reservoir, the synthetic CPM eco-train. We are plotting the ecos, so we are effectively plotting is like the sound is like the sound of hydrogen recorded by the nuclear magnetic logs. When you shift, when you make to, if you are remember the presentation, when you shift to this, to 1 2-second measurement system, to 180 angles degree RF, when you shift to 180 RF pulse, apply the T-time flips, the spin across the transverse axis to reverse the phasing. So it's like effectively to the sound of hydrogen. The T2 logarithmic inversion, what allows this graph is the hydrogen reservoir signature. Hydrogen reservoir signature with plotting NMRLog amplitude and T2 relaxation time. We have a signature, a clear signature between 10 elevated second and 10 elevated to 30 fraction 2. We have also the hydrogen Akiva model saturation. How hydrogen after the diffusion model, how hydrogen saturated the rocks, which is the percentage of hydrogen that saturated the rocks by plotted by depth. So you have also reconstruction of the presence of mineralogy by estimation of percentage serpentinite, magnetite, brucite and carbonate in this percentage. Hydrogen generation potential, serpentinite water rocks reaction, Mg silicate hydrogen, magnetite is this, brucite is alkaline reaction environment. So it's clear the brucite have a conductant and alkaline environment reaction, while serpentinite was water-driven reaction. Carbonate is sealing and buffering. We are plotting finally the NMR plus alkyl with the saturated model plus mineralogy index in this case, DAF, and NMRLogs hydrogen reservoir summary. So you have the reservoir is between this DAF, dominant system is the serpentinite, NMRLogs relieve long two-time relaxation, so it will be probably if you have a plan, reinjection system, you are a closed system that will be, if you are not damaged reservoir, a closed system that can be function for 100 years or similar. Seals is made up by the limestone. Surface cover is made by claystone between a depth between 0 to 100 meters. Integrated evaluation, CPM. What we are doing with CPM echo, with CPM echo, we are simulating the NMR curve Purcell Gill acquisition. We generated the case curve from different two-time relaxation. So, as we just say in the presentation, to isolate the real value, we need to have the echo train that is effectively to the sound of hydrogen, because you need to separate this with this phase, with the phasing from the brucite and magnetite effects, and make purge noise and inversion response. After you have also the 2D logarithmic inversion and the clay bound hydrogen. Finally, you have also the serpentinite hydrogen reservoir detection, the 2D NMRLog T1, T2 relaxation time correlation map. So in this map, in this slicing map, you are correlation the two-time relaxation time in milliseconds and 2-1 relaxation time milliseconds, and you are plotting the positioning of reservoir. So that is represented the effective where hydrogen reservoir is collocated as ratio between this value, and also the free fluid cutoff. So the free fluid cutoff is established to this value, but effectively the hydrogen reservoir have this value is near is less than 1 between ratio T1 and T2. We have also the clay boundary water, the limestone caprox, the hydrogen reservoir. You have the claystone T1, T2, and interpretation boundary water, low mobility. So T1 claystone is this. Have this. If you have this interpretation, claystone have T2 relaxation time minus than 10 milliseconds. Interpretation is a bound water, a low mobility layer, so it is not possible diffusion of hydrogen, clear. The limestone have this this value of limestone cap rock. Interpretation is a capillary water, low permeability seal. So limestone cap rock have a T2 relaxation time near to 18 milliseconds. Serpentinite hydrogen is similar to this. We have a free hydrogen signature, the high mobility, long relaxation, high diffusion, connect pore fracture system. Hydrogen reservoir domain detection is the reservoir detection is in the fourth quadrant. So serpentinite hydrogen reservoir sanded find between 118 and 300 meters. You have molecular phase, fracture control, accumulation and high mobility. In the last part you are producing the diffusion map that show the behavior of reservoir hydrogen versus water separation. Why hydrogen versus water separation? Because it's much more important to underline the different phases. So how easy, if you are working with 5 liter, you need to separate free hydrogen from water. Extracted molecular hydrogen domain. To extract the effective hydrogen domain, you need to have a coefficient of diffusivity between 10 elevate minus 9 and 10 elevate minus 8. The second time you have the 2-time relaxation between 10 elevate 30 and 10 elevate 4. Diffusion, so the log is that. Diffusion log show this behavior and drastically increase under this 100 meters 18 depth that represent the reservoir, and NMRLog 2 tools, NMRLog second times relaxation is the same. So the hydrogen detection is clear that major part of hydrogen is concentrated in this 30 or 40 meters depth, starting from 118 depth, and you have some free part in the brucite seal. Diffusion and major hydrogen interpretation. How is the hydrogen is which is the diffusion model elaborated by NMRLogs. Claystone have this diffusion and 2-time relaxation at 5 milliseconds interpretation. No possibility of hydrogen mobility. In the limestone, you have this value of diffusion. The interpretation is a carbonated water and seal interval. Serpentinite reservoir, you have this kind of value, and the interpretation is free molecular hydrogen, high diffusion, long relaxation, connected fracture, mobile gas phases. You have the connected fracture and mobile gas phases. So this is a complete interpretation of NMRLogs in this geological context for reservoir hydrogen classification with ductile technologies. Remember, with ductile technologies, because the time space in the interval is not too equal and sufficient to appreciate the molecular, all of molecular hydrogen. So we need to work on this. Finally, you have the magnetite, also the magnetite sociability correction. It's much more important phases of processing the NMRLogs. You are recording the depth, the presence of magnetite in this first graph. The presence of magnetite is depth, magnetite is sociability part per million in depth, and you have the NMRLogs to magnetite correction. we underline that you measured the two-time relaxation. So the measured two-time relaxation is blue, but the correct value is corrected by this orange value. Magnetite correct. Why is much more important to have the effects of magnetite? Because it influences the hydrogen index. You have an observed hydrogen index that underestimate this because there is the influence of magnetite. The corrected index of magnetite, you have this final value that is seems to the first curve to the hydrogen, the real corrected hydrogen index. What does it mean? That magnetite NMR correction, you have 0 magnetite in surface first layer, claystone. You have the 5% in 1% in limestone. In limestone cap rock you have the 1% and you have the the effects of this 1% in this, you have the effects that small 2D reduction and still good seal indicator. So you reduce the 2D, the two-time value. Serpentinite hydrogen reservoir, you have a percentage of magnetite between 10 to 14%. Affect strong local field gradients. Observe what does mean that you observe the second two relaxation time is shortened. So reaction stores true pore fluid of relaxation time, free hydrogen index, high, and that means free hydrogen index and also high elevated mobility of hydrogen. Final reservoir parameters. You have corrected the two-time relaxation time higher than measured, so in this case is higher. Corrected the FFI, so higher than apparent FFI. Hydrogen potential, you are making an underestimated without magnetic correction. So magnetic correction given the real values of hydrogen potential in this case. Finally, we have integrated wireline. For integrated wireline log results, NMR, natural hydrogen reservoir, you have the sonic log, resistive logs, and plotting all of the data with the gamma ray logs. The integrated hydrogen reservoir interpretation. So this is the integrated for limestone cap rock. You have interpretation carbonate mechanic seal, T2 relaxation between this value, high density, GR value, gamma ray value is low. For serpentinite rocks you have high density, high resistivity, sonic fracture lifts, and FFI measured than 50%. Interpretation is free molecular hydrogen reservoir. So we goes on to the project.